All right. Same thing as always. But at this point, it's looking like it's every day. But don't feel like doing shit. But I gotta do shit. Um, so yeah, I'm probably gonna be doing like a what's the method called, like Pomodoro or something. But it's like 11:10. So I don't even know how long I can do it for. Hopefully I don't go like don't take too long. So yeah, I guess I did like 10 lead codes today. I'm still going through uh, the blind 75 while at work. So it's just catching up to, um, or it's just doing the math part that's really that I gotta. I don't know why I came back from work like 7:30. Anyways, who gives a shit? Um, Last time I skipped two problems because I didn't feel like it. I don't see how I can use like my brain power to like you all like I'm not even reading this, but like this looks long as hell. Same thing with the next one or like the application letters. Oops. Yeah, that also like spills over a whole page and a half in a bit. So I am low-key good. This is where we left off this cubic integers one. I think I just zoned out on this problem, but I think I like sorry. I think I misunderstood this problem. Uh, so yeah, um, yeah. I just feel really restless right now, like, and tired at the same time somehow. But like, we're gonna see what happens. I'm just reading the solution, seeing what's going on here. Interesting. Okay. Okay. Yeah, I don't know what I was just staring at. Right, we're gonna be doing 4.3. I think I'm on page 73. Yeah, there's still like 30 pages or something to get through, but like, I'm not gonna be worried about that because I'm just gonna read the theory and stuff. Pretty much know this already, but probability of A given B is probability of A and B over probably. I've never seen this notation where they say A B, but yeah, fair I guess. Over probability of B, which makes sense. I mean, yeah, probability of all of these is like E1 and then E2 given E1 and then E3 given E1 and E2 and then oh okay yeah oh alright goddamn alright maybe it gets a little exciting when I get to the problems. Total probability so oh wait hold up, probability of E is E in F1 plus E in F2 plus E in F3, yeah, which is a summation of yeah that makes sense. Like the probability of, let's say, rolling a 6 is the probability of rolling a 6 and, let's say, like rolling an even plus rolling an odd. Oh sorry, not rolling a 6, what am I saying? Probability of just, I don't know, like any number showing up which is 1 is probability of even plus odd. Yeah, like I don't, I'm pretty shit at explaining it, but I mean it's pretty obvious. It's just like yeah. For any mutually exclusive events though, so they can't be like that makes sense. uh, what the hell is FC, that complement? Oh okay, yeah, I'm stupid. Bayes formula is probability of A given B is, oh wait hold on, what is this? Oh okay, I guess this is a more like, okay, so probability of like any F given E is E given F times P of F over um, I'm assuming probability of E, but probability of E is like you get this, oh sorry, the denominator from this, like up here. Um, but yeah, a trick is to like imagine that this is a fraction, and then you get P of E, so P of E times, you know what I mean. I guess that's a stupid trick. Okay, that is okay. Part A, okay, boys and girls. Okay, a company is holding a dinner for working mothers with at least one son. Okay, Miss Jackson, a mother with two children, is invited. What is the probability that both children are boys? So let okay, probability that both children are boys. So um so yeah, so again like event A would be, let's say um let A be the event that like uh A is the event that they have like someone is invited. Is that like a valid event to have? Let's do that, right? Let's A be the probability of being invited, which is essentially the probability of having at least one son, and B be the probability of two children. And I guess two sons, sorry. And then it would, I feel like you also need a C for like, what's the probability of having a child? Yeah, so I don't think that makes sense. Like probability of having a child. So I can't do C where it's like two children. Um, so probability of B, given that she has at least one son, is probability of A and B, which is, let's say you already have at least one son. Probability of having two sons. Okay, probability of having two sons and at least one son is just probability of having two sons. So that is that not just 1/4 A and B over probability of A, which is having at least one son. So at least one son when you have two children. I think this is what we have to assume. Let's say you have two children. At least one son, it's like 3 of the 4 cases. So 1/4 over 3/4, so that's 1/3. Yeah. Okay, cool. Your new colleague, Miss Parker, is known to have two children. If you see her walking with one of her children, and that child is a boy, what is the probability that both children are boys? I remember seeing. Wait, this is actually interesting. I remember seeing like a YouTube video about this, but like it was like 2, 3 a.m. or something. So like I kind of forgot what they were talking about. But let's see. So everyone knows. Okay, it's two children. If you see her walking with one of her children, and that child is a boy, what is the probability that both children are boys? So let A be the event that both boys. Is it just 1/2 here? I feel like it's just 1/2 here because here the fact that like okay, here the fact that what is the probability that both children are boys? So like in the first part, I feel like it's like the chance was increased because we know that at least, so knowing that at least one is a boy increases it, but like here you don't know that at least one is a boy. You know that like you only know one is a boy, if that makes sense. I don't know, this one just seems like 1/2. Yeah, notice that. Yeah, I want to see the explanation. Like I can't explain it, but okay, wait, let me try to explain it. I'm not gonna read the solution. This might be a waste of time, but like I still want to do this. A company's holding, yeah, so working mothers with at least one son. So like you already know that like they have at least one son. You don't know if they have one son or two sons. You don't know. But you know they don't have zero sons. I guess, but it's the same thing here. You know that it's one son. Oh, you know what it is actually? Hold on. So let's like label the kid like kid one and kid two, right? Like assuming, because they're, I think another thing is that they are they are distinguishable, right? Let's say this was like instead like just red ball and blue ball, right? Where the balls are like indistinguishable, right? So like the probability then would be, so in the first case would be probability of B, A and B, which is just probability of B, which was probability having two red balls, let's say, which is 1/4, over probability of uh, A having at least one red ball. But like like let's say they were indistinguishable. What is the probability of having? Would that still be? That'd be 1/3. No, that doesn't make sense. Oh, sorry, no, 2/3. I mean, no, that also doesn't make sense. Okay, now I just confused myself. Okay, what the hell? But what about part B? It's just you know that like one child is a boy, but that tells you nothing about what the second child could have. Like because the second child is mutually exclusive in this scenario. Uh, yeah, I don't know actually. That's interesting. I want to see what the explanation is. I can explain this. Notice in part A, the problem essentially asks if there is at least one boy. What is the condition? Part B asks that given one child is a boy. Wait, given that there's at least one boy, given one child is a boy, like one specific child is a boy, what is the conditional probability that the other child is also a boy? Yeah, I think that's it because like you're being specific about the child here, right? But if you were to say like, hey, I know that one of them is a boy, right? Then what is the probability? Then that changes it. Yeah, yeah. Okay, so because I think here, like when you do P of B, like right, instead of BG and GB, this GB part goes away. It's just BG because the first one is already fixed. So now your sample space is reduced by, yeah. So it's just these two cases. So 2/4, 1/2. Yeah. Okay, that's good. Good stuff. Oops. Let me go to the next one, please. All right, all girl world. Okay, let's see. In a primitive society, every couple uh, prefers to have a baby girl. There's a 50% chance that each child they have is a girl, and the genders of their children are mutually independent. If each couple insists on having more children until they get a girl, and once they have a girl, they will stop having more children, what will eventually happen to the fraction of girls in this society? Um, I mean, that cannot be good, right? Because, like, you expect to have two children. Oh, wait, it might just stay the same, actually. Because I think you expect to have two kids, right? And I think you expect to get a boy and a girl. So I think it's the same. Yeah, okay. I was gonna say 50%. Yeah, they stay the same. Okay, wait. I actually got that then. Nice. Um, But yeah, I don't know. It says like do not let the word prefer and the wrong. Yeah, I mean that didn't. I was just thinking about it in terms of like an expected value type of thing. The fraction of baby girls are driven by nature, or at least the X and Y chromosomes, not by the couple's preference. Yeah, of course. You only need to look at the key information. 50% independence. Yeah, yeah, okay, fair. Okay, I didn't read the solution. Yeah, okay, the solution's on the top right. Cool. You're given 1,000 coins. Among them, one coin has heads on both sides. The other 999 coins are fair coins. You randomly choose a coin and toss it 10 times. Each time the coin turns up heads. What is the probability that the coin you chose is the unfair one? Okay, this is fine. Um, so probability of let A be the one where it's probability of unfair, and B be the event of uh, like 10x heads, right? Probability of A and B is just probability of um, oh yeah, so probability of A given B is, hold on, yeah, probability, okay, I'm messing up, whatever. The probability of A given B is the probability of A and B, which is probability of unfair. It's just probability of getting the unfair, uh, which is 1 over 1,000 over the probability of B, which is what is the probability that you get 10x heads. So now here are the two mutually exclusive events, F1 being the event where you get the unfair, and F2 being the one where you get any other coin. So then you do probability of like I could just like intuitively just like speed run this question already, but I just want to make sure that like whatever I'm doing like makes sense with the actual theory. So the probability of B, as we know it, is the summation of uh, like B given F1, the summation of B given F times probability of F. So in this case, probability of B given F1, which is 10x heads given unfair, which is just probability of unfair, so 1 over 1,000, plus probability of B given F2, which is like probability of 10x heads and um, any like heads over probability of getting the heads, right? So right, right. Did I get that formula right? I'm sorry. I just want to make sure. Independent events. Yeah. Okay. They are mutually exclusive, but is F independent of B? Probably not. So, yeah, this is essentially what I was kind of doing, except I just did P of A and B up there. Okay. I'm doing a pretty sloppy job, but like, hold up. P of 10x heads. I'm just really trying to make sure I do it with the formula, because I like structure. Um, given any. So given, so divided by 99.9 over 1,000. And on the numerator is 10x heads. Probability of 10x heads and like I'm doing like the total probability theorem. So like intuitively, I just want to do like that divided. Okay, let me just do it intuitively. Hold on. So I would just do 1/1000th over 1/1000th plus 99,999 or 1/1000 or whatever times the probability of actually uh, getting 10 coins. So that would be 1/2 to the power of 10. Is that it? So like, so that's like 1 over 1 plus 999 over 1024. So 1024 over 2023. Yeah, this is what I did. Yeah, this is what I did. Hold on, but let me see the formula way he did it. Yeah, so let A be the event that the chosen coin is unfair. Yes. And AC is the event that, yeah. And let B be the event that all 10, yeah, that's exactly what I did. Okay, then that is P of A given B. Okay, so they use this one. I did like P A and B over P of B, which I think is the same thing. It's the denominator that like, but I think A and B, you can only do it if you know that it's like mutually exclusive or whatever. But yeah, okay. But P of B given A times P of A. You know what, let me do it this way, right? Probability of B, which is 10x eds given unfair, is 1 times, oh wait, I think that's what I did, but like intuitively. Over P of B given A times P of A, yeah, plus P of B given AC times P of AC. Interesting. Oh wait, I think that's not what I did then. Like in the denominator, I was trying to do times probability of. Is it, wait, what the hell was I doing? I'm actually confused. Given any. Yeah, no, that was what I was doing. I don't know why I was like stuck on it. So given that I got an unfair coin, what is the probability? Yeah, that's just, yeah, I don't know why I was stuck on that. Like I literally had it, but like I was just confused. But yeah. I don't know. Yeah, I think that's like like a peak indicator that like I am not like in the right mental space. All right. If you have an unfair coin which may bias toward either heads or tails at an unknown probability, can you generate even odds using this coin? I remember like seeing this problem like earlier when I applied for my school's quant club. Look. I think it's like yeah, I think you just flip it twice and you only consider head tails as one event happening and tails as one as your new head, if that makes sense, and then tails head back to back as your tail event happening, if that makes sense. Yeah, this is, yeah, pretty much. Okay, wait, how long is this one? I just want to make sure it's not that long. Actually, you know what, whatever, I'll still do it. Jason throws 2 darts at a dartboard, aiming for the center. The second dart lands farther away, or farther from the center than the first. Okay. If Jason throws a third dart, aiming for the center, what is the probability that the third throw is farther from the center than the first? Okay. Okay, I low-key feel a bit fried, like just off of thinking about that. Yeah, I think my brain's actually at its capacity, so I actually might straight up call this today. This like really dog shit. Like I did what, like one, two, three, four problems. Yeah, this is pretty shit. But like I'm gonna cut my losses and call it here. I don't think I'm like doing this shit. Hold on, let me just look at this. Yeah. Oh wait, this one. I swear I've seen this one. This problem, but that was on Open Quant. I think I remember seeing this. Um, I'll just try to do some short ones because four problems seem like really like stupid. Okay, I'll just do this one, I guess. We throw three dice one by one. What is the probability that we obtain 3 points in strictly increasing order? 3 points? What? Oh, you mean like three results, I guess? Like it's not like the physical dots you connect? Okay, strictly increasing order. Okay, so they first of all, uh, three dice. Wait, how's this Bayes theorem though? I don't think this is Bayes theorem, right? Is it? Oh, it is, I guess. But like, okay, so they have to be. I've done this problem before as well, I think. So like, they have to be unique. So six choose three over. So yeah, so six choose three ways to pick your thing. So 6, 5, 4 over 6. So that is 20 ways to pick your thing. And then only a sixth of those are the correct order. So yeah, 20 ways to pick that. So the probability that you get like three distinct numbers is 20 over, damn, that's a big number. 20 over 216. Dividing it by 4, we get 5 over 54. Um, so like, is that right? 6 choose 3? Times 6, I think, because I can get like 6 orders of like just amongst each other. Like, yeah, and then divided by 6. Okay, yeah, and then 5 over 54. Okay. Yeah, valid. Okay, so I know this problem as well. Okay, these are, wow, I didn't know Greenbook had so many classics, but yeah, this one I like just off of like reading the American show, like I know what problem this is already. But given three choice of three doors behind one door and nothing, you pick one of the doors and announce it. As soon as you pick the door, Monty opens one of the other two doors that he knows has a goat behind it. And then he gives you the option to either keep your original. Yeah, so I think like initially you have a 1/3 chance of being right, but now that he got rid of it, that new door he has a 1/2 chance of being right. So it's actually, yeah, yeah. So yeah, genuinely, yeah, switches it. Oh, sorry. Yeah, no. So it doesn't even have one chance. It has 1/2. Sorry, that's 2/3. Yeah, because okay, yeah, that makes much sense. Yeah. Okay. I don't wanna. Gambler's Ruin. Ooh, nice. I know. I know. That's like a. It's like a thing. Um. Wow. Okay, wait. The open quant ones actually have like a lot of like similarities with some of these. That's interesting. I was like thinking of doing like this problem, except it was like for soccer or something. So like interesting. Um. What kind of weird specific number is this? Is it because like 625 minus this is 16, and that's like a really nice number that is like 4 over 25 squared. So yeah, like I don't know, yeah, that's interesting. Okay. 16 over yeah. Yeah, that's interesting. Yeah. Assume that the probability of seeing the yeah. Okay, then this is just that. Yeah, I'm just like rotting and like going through this. I'm not really doing anything valuable. So I did like what, like 5, 6 problems or something. You know what? I know like half of them I like knew already, so like doesn't really count, but gives me a sense of accomplishment. All right then. Yeah, that's about it. I will, yeah, end the video here.